Hello everyone, I'm Yi-Lin, and today I'm going to show you how to model acoustic systems in the Wolfram language. And the modeling process is based on solving a set of partial differential equations. So let me introduce a bit what a PDE model is. So a PDE model is a set of mathematical equations that can describe the physical phenomena in the real life. So for example, in acoustics, we use wave equation to describe the sound wave in time. And in fluid dynamics, we use Navier-Stokes equation to describe the flow field. And with all these mathematical equations, we can build PDE model for the computer simulation. But one difficulty in solving a PDE model is that most of the time, we are not able to get an analytical solution because the complexity of our system. But in the Wolfram language, we have many powerful building functions, such as undissolved. They can do such tasks for you. They can use the finite element method or finite difference method, depends on what you like. So as a start point, we are now developing the tutorial in acoustics to show users how to build acoustics model in the Wolfram language in Mathematica. So in the following sections, I will show you how to build acoustics models in the Wolfram language and to, for both time domain and frequency domain analysis. And I will show you how to set the acoustics PDE, how to model sound sources and various types of sound medium. And I will also show you how to use the building function in the Wolfram language to map the acoustics boundary condition in our language. But before we jump into each step, let me give you a sense of the whole modeling process. So for example, we are modeling a muffler, an automobile muffler, and we are interested in the performance at different frequencies. So we perform the analysis in the frequency domain, and the modeling process can be divided into 5 steps. First, we have to define our domain, and then we specify the boundary conditions. And we set our PDE model, and then we solve our PDE model numerically using the building function undissolved. And finally, we can do post-processing and the visualization to check our results. So consider another case. If we want to study the sound propagation in time, the whole modeling process is very similar. The only difference is that besides defining the boundary conditions, we also have to give the initial condition of our simulation domain. So in this example, I'm showing the sound diffraction pattern in the 2D domain. And let me show you the result in Mathematica. Here it is. So we can study the diffraction pattern. So okay, now let me show you how to define the acoustics PDE in the Wolfram language. So for the time domain analysis, we use wave equation as our PDE. And the primary variable is the sound pressure, P, here. And rho stands for the density of our sound medium, and C stands for the speed of sound. And F and Q stands for the optional sound source we can add to our acoustic system, which I will explain a little more in the following section. And in the frequency domain, we use Helmholtz equation as our governing PDE. So unlike the wave equation, Helmholtz equation is a stationary equation. And there's an angular frequency term in our Helmholtz equation. And you may notice in both equations we have a common part, and I highlighted in blue. So in the tutorial, we have already defined a help function called acoustics model. So as a user, you can define both PDE with only one line code. So next, I will show you how to model sound source in the Wolfram language. And the two common sound sources in acoustics are monopole source and dipole source. So a monopole source is a point source that radiates the sound isotropically. So let me first show you what it looks like. It looks like this. So to define the monopole source in the Wolfram language, we have to add an extra term when we define our PDE. So the monopole source denotes by the symbol Q here. And it's equal to the amplitude of the source and the direct delta located at the source location. But as a user, you only have to define the amplitude of your monopole source as well as the location and the frequency of your source. We already defined a help function for you to do the calculation here. And oops. And then in this example, I demonstrate the result in the time domain. So the setup of the PDE, the code here, corresponds to the upper equation, upper formula. So the frequency domain, one is just for reference. And yeah, so let's see the result again. And the plot at the right is the sound amplitude distribution. So the sound has the maximum values near the source location and decays as it propagates far away from the source. So how about the dipole source? Unlike a monopole source, the dipole source didn't radiate the sound isotropically. So let me show you. So if you want to define a dipole source for your acoustic systems, you have to define the amplitude of the dipole and the source location, the frequency. But you also have to define the orientation of your dipole source. So here, in this example, I define the orientation as 45 degrees. So the modeling process is very similar to modeling a monopole source. You also have to modify your PDE. And the dipole is denoted by the symbol F here. So we also have a help function to do the calculation here for you. And here is how we set up our PDE with the dipole source. So because I set the orientation as 45 degrees, you can see the amplitude of the dipole source has the maximum value along the line in 45 degrees in this plot. So next, let me show you how to model the sound in various types of medium, including in the Wolfram language, we can model the sound in homogeneous medium and in homogeneous medium. And we can also model a lossy media where the sound keeps decaying within the domain. So as an example, I will show you how to model the sound in a lossy media. So to build this model, we have to add an extra dissipation term when we define our PDE. And I highlighted in blue. And this dissipation term is defined by the flow resistivity and the porosity of the lossy media. And the modeling process is, the first step is we define our domain. and we set up our modified version of the PDE, which equals to the original PDE plus the extra term, extra dissipation term. And here, I set up a boundary condition to produce the incoming sound wave from the left. And we solve it in ND-solve, and let's see the result. So as you see, the sound keeps decaying as it propagates through the domain. Okay, so next, let me show you how to use the building function in Mathematica to map the acoustic boundary conditions. So the acoustic boundary condition can be categorized into 3 types: the Robin-Neumann type and the Dirichlet type. For Robin type and Neumann type, we can use the building function called Neumann value to map these boundary conditions. And for Dirichlet type of boundary condition, we use the function called Dirichlet condition. So let me show you an example how to map the impedance boundary condition in the Wolfram language. So but let me introduce what impedance boundary is and what is the purpose of using it. So imagine we are modeling a sound propagate from one material to another. Because the density and the speed of sound are different, when the sound propagates across the medium, some part of the wave will be reflected and some part of the wave will transmit through the interface. So looks like this. Yeah, but so we can build this model in Wolfram language, and we define the domain consists of both medium 1 and medium 2. But what if we only interested in the region of medium 1? It will be very inefficient if we build the whole domain consists of both medium 1 and medium 2, but we are not interested in the region of medium 2. So in this case, we can use the impedance boundary condition to model the median interface here, so that we can only, our computational domain only consists of the median 1. And here is the formula of the impedance boundary condition. But I didn't put the derivation here because it will take like 10 more pages. But if you are interested in the derivation, we have put all the derivation and explanation in our tutorial. And you can always refer to that. So we define the impedance boundary condition using the building function Neumann value here, because impedance boundary condition is a Robin type boundary condition. And let's see the result. So our result is exactly the same as the left-hand side of our previous animation, but now it is much more efficient because our computational domain is like only in medium 1. So last, I'd like to introduce a modeling method called perfectly matched layer and how we implement this in the Wolfram language. So perfect PML is a method to model the simulation domain with infinite extension. So imagine we are modeling a sound wave coming from left and to the right and all the way down to infinity. But clearly, we cannot have a simulation domain with infinite extension. So if we simply truncate our domain and do nothing at the boundary, then the result will look like this. The wave will be reflected to our domain and interfere with the incoming wave. So to solve this issue, we can use the PML. PML is an extension region attached to our original simulation domain. And within the PML region, the wave will be attenuated so that at the boundary, the wave didn't reflect back to our original domain. So it looks like this. So if you focus on our original simulation domain, it looks like the wave propagates from left to all the way to infinity. So yeah, to implement the PML in the Wolfram language, we have to modify our PDE. So the black part is the original PDE. The part highlighted in blue is the extra term. So S here stands for the variables that control the attenuation within the PML region. And it depends on the sigma, which is the absorbing coefficient. And this is chosen by users. So the modeling process is the same as previous. The only two things you have to do is you have to enlarge your domain to include the PML region. And then you have to set the PDE with the transform version here. So now let's put everything together and do an application example. So this is the muffler I should show you previously, but now we will go through the modeling process step by step. So first, we define our 3D domain, and here I use the Boolean operator to define the domain. And then I set the boundary condition. In the inlet, I use the radiation boundary condition to produce the incoming wave. And at the outlet, I apply an absorbing boundary condition to avoid the wave reflection. So then I solve our PDE model using the parametric ND solve across the frequency range I'm interested in. So now the frequency range I want to study is from 15 Hertz to 1500 Hertz. And now we got the result, and we can visualize our result. So the left plot is the sound distribution within the muffler. You can see the amplitude at the inlet is high, but at the outlet, the sound has been dissipating by the muffler. And yes. And one property to quantify the performance of a muffler is called transmission loss. It calculates how much sound has been dissipated by the muffler. And here is the formula, which you can find in many acoustics books. And after some calculation, I got the plot here. And based on this plot, I can know at which frequencies the muffler do the job the best. And based on this, we can also improve the design of our muffler. And if you are interested in the eigenfrequency and the eigenmode of your system, you can solve the PDE model using the building function called ND eigensystem. And you gave the function how many eigenfrequencies and eigenmodes you want, and the output will be a list of eigenfrequencies. And here is the visualization. So this is pretty much how we model an acoustic systems in the Wolfram language. But acoustics is just the start point of our project. Our ultimate goal is to apply the Wolfram language in many other areas. So we can help users in each specific field, and they can build their models and do the analysis in the Wolfram language. So thank you very much for attention. Which field do you think we should do the next? And if you have any questions or comments, please, you are more than welcome to send me an email or ask me next. Yeah. Thank you very much.